Hello and welcome to Sunday's edition of Cracking the Cryptic. A very happy Father's Day to those of you who celebrate such things. Today's puzzle has an interesting history. It was sent to us by one Aaron Rodgers, who we know to be a very, very famous NFL quarterback. Now, that might have been the end of it. We often get sent submissions that seem to be from celebrities. But Aaron's pseudonym is GB Pack, a name that I know will be familiar with you if you've been following the Sudoku scene for any amount of time, because GB Pack has been producing some incredible puzzles with amazing ratings over on Logic Masters Germany. But GB Pack, of course, is short, it seems to us, for Green Bay Packers. So well, and of course that's who Aaron Rodgers plays for. So it just could be. We don't think it is, but it could be. And wouldn't it be amazing if it did turn out that the quarterback, Aaron Rodgers, is setting puzzles that are amazing the Sudoku world? I'll read you the rules of this one in just a second. It's called Arrows and a Big X. Over on Patreon, what have we got? We've got the solution video for our Hitchhiker's Guide to the Galaxy Sudoku hunt. So do have a look at that if you've not had a chance to, or if you got stuck on the solve, I suppose. And also remember, I think tomorrow we plan to release Zeta Math's video on how he set Sudoku, and that is definitely worth watching. Very, very interesting video indeed. Now with that, let's get to it. What are the rules of this puzzle? Which I believe, by the way, is quite difficult. The testers say this is a stunning puzzle, but not easy. Well, what are the rules? Normal Sudoku rules apply. Digits along arrows sum to the number in the circle. So that means those 3 digits there, you add them up and you plonk it in the circle there. And numbers do not repeat on marked diagonals. Right, so we've got 2 diagonals here. I didn't put this in the software, by the way, but if I do get a chance, I may actually change it so that these diagonals are in blue, so they're a bit more visible. But anyway, we can't repeat digits on these diagonals, so don't do that. These have got to contain the digits 1 to 9 once each. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And right, well, let's start by saying it is a little bit absurd that this has a unique solution, because there is almost nothing in this grid at all. We've got the strange sort of shape of arrows emanating from these 4 circles, 2 tiny little arrows which look to me like disambiguating arrows, and a marked diagonal, and that is it. That is crazy. I am slightly worried I've been given a bad puzzle here. This surely cannot solve. We'll give it a quick go, and then we will probably find out that there is either an arrow missing or a knight's move constraint missing, or something like that. What I can see immediately, obviously, is the obvious thing about arrows. If you've been doing arrows puzzles for any amount of time, you will know that 3 cells on an arrow, which must all be different digits, so the minimum we could make these 3 cells is 1, 2, and 3, means that this cell here must be at least equal to 6, because it's summing those digits. And the same is true for each of the arrows, look. So these circles have to be at least 6. Now I'm actually wondering about this cell. Is that a sensible cell to think about? The answer is perhaps. What I'm thinking about is how many repeated digits you could have in those 3 squares and those 3 squares. And the answer is 1. Because if you have more than 1 repeated digit, where would you put them in box 2? This is actually quite interesting. Maybe this is why this puzzle solves, is because it's more constrained than I first realised. Let's just think about this. 2, 3, 4, 5. Right, yeah. Here's a simple deduction. Let's start with simple deductions and go from there. How many digits have I just highlighted? 6. Is it possible all 6 of those digits are different? No, because if they were all different, they would sum up to 21 at least. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. But that would mean these two squares have to sum to 21 at least, and they can't. The maximum those two cells could sum to is 17 if we make them 8 and 9. So we know that there is a at least one repeated digit in these squares. Otherwise they're going to sum up to too high a number. Now, there can't be two repeated digits, actually. I'm just thinking about that. I was wondering whether you could repeat 6 on the arrows, but you can't for many reasons. First reason is that the totals would get too high. The second reason is that these would both have to be 9, because if you put 6 on both of those arrows, 1 plus 2 plus 6 is 9, and that would be the minimum we could make those 3-cell sequences add up to. So this would be double 9, which doesn't work. So if you can't repeat 6, and you can't, how many repeated digits can there possibly be? Only one, because there is only room for one. You obviously, whatever you repeat in those, whatever's in here and in here, will only be able to go in here, because it will have to be lower than these circled digits. Because the maximum digit you can put on a 3-cell arrow is 6. So this square is restricted, and it's equal to the repeated digit which we know exists, we just don't know what it is in these little regions. 15, 15. Ah, right, this is a 1 or a 2. Here we go. How do I know this is a 1 or a 2? Well, let's remember that the maximum size of those two squares is 17. If it's 17 in these squares, let's think about what's the minimum I could make 5 of these cells add up to. Given we know that there are definitely 5 different digits in these 6 cells, 1 plus 2 plus 3 plus 4 plus 5 is 15 as a minimum. So if the repeated digit was 3, that would mean that the 6 cells would add up to a minimum of 18, which they can't do. So the repeated digit is a 1 or a 2. And we don't obviously know which way round the 8 and 9 go. But we do know that the same logic must apply at the bottom of the grid, because it's it's not symmetrical. Well, it is symmetrical so far as 1s and 2s are concerned. It's symmetrical so far as this square is concerned, but I've just noticed it's not actually symmetrical. This arrow is not symmetrical. That's weird. Look, that arrow, it all looks perfectly normal and like it's just mirror symmetry. And then this one is sort of offset and twisted. That's odd. Okay, but this square's got to be a 1 or a 2, exactly the same reasoning as for up here. I have a strong suspicion that these are going to all be different. This is what's making me wonder whether there's a Knight's Move constraint in this puzzle, because if all of these cells were different, they would all see that by Knight's Move, and this square could only be a 3, 4 or a 5, which looks quite interesting. I hope somebody's not messed up here. Now, can we do anything else with this? Well, we're going to have to, because I've got absolutely diddly squat in terms of real deductions here. I know that these have a maximum value of 17. There's either a 1 or a 2 repeating. And there can't be both. Oh, now hang on a moment. If you put 1, 2 and 3 in, 2, 3, that doesn't work with 7. It doesn't. Ah, right. No, I've got this completely wrong. I am completely wrong. Why am I wrong? Well, I'm wrong to say these are 4 different digits. I can prove they're not. None of these digits is a 6. Why is none of these digits a 6? Let's work it out. A 6 would have to be 1, 2, 3 on its arrow. Now, what are we going to put on this arrow such that there is one repeated digit and not more than one? Because if this was 7, for example, and this was 1, 2, 4, now you can see we've got a massive problem with the puzzle, because we've got a 1 and a 2 in this triple, we've got a 1 and a 2 in this triple, which means in row 3 we need to put a 1 and a 2, and there's only one cell that can take those 2 digits, so it's broken. So you can't put 7 in here. What about 8? Well, again, we've got to get one repeated digit. The 1 will repeat if we put 8 in here, because you always have to have an 8 in a 3-cell sum. And whether we go 1, 2, 5 or 1, 3, 4, the 2 or the 3 will repeat, and that breaks it again. What about 9? Oh, it's not Maverick today, it's a motorcycle. What about 9 in here? Well, how do we avoid 2 repeated digits? 2, 3, 4 won't work, that repeats the 2 and the 3. 1, 3, 5 won't work, it repeats the 1 and the 3. And 1, 2, 6 won't work because that repeats the 1 and the 2. So you can't put a 6 here. And if you can't put a 6 here, you can't put a 6 here, 6 here, or 6 here. So this is actually 7s, 8s, and 9s. Which means that is not 1, 2, and 3. Yeah, this logic is interesting, actually. Yeah, this is gorgeous. Right, let's keep going with this. Is this a 7-8 pair? The answer is no, it's not a 7-8 pair, because let's try this. If this is a 7-8 pair, we know that the 7 arrow will be 1, 2, 4. How do we avoid 2 repeated digits? You can't. Because if the 8 will either be 1, 2, 5, you've got a 1 and a 2 repeating, or 1, 3, 4, you've got a 1 and a 4 repeating. So 7 and 8 is impossible in the circles. And if 7 and 8 is impossible in the circles, there's a 9 in one of these 2 cells. And therefore there's a 9 in one of these 2 cells, because the logic just works the same way at top and bottom of the grid. So now I'm wondering whether 9 has... Oh, 9, I tell you what, one thing, we can ask where 9 goes in column 5. 9 is not there and it's not there, so 9 is in one of 3 cells in the central box. And I was actually wondering where 9 is going to go in all of the side boxes of the grid, because 9 now can't go there. 9 can never be on a 3-cell arrow, so we're going to be restricting... Yeah, there's a massive restriction on 9s in column 3. The 9 can never go on an arrow here, because 9 plus 1 is at least 10, which we can't put in a Sudoku. So there's a 9 in one of those 2 squares. I almost wish I hadn't just got rid of that highlighting. That was quite interesting. Let me go back. 9 on the right-hand side of the grid is different, though, because of the strange geometry of this arrow. I haven't used the diagonals yet at all either. It's making me think about Fistimofel, this, which actually that might not be such a silly idea. Is there something going on with... I had this thought yesterday and it turned out to be complete nonsense. Fistimofel obviously is the theorem that states that these 16 digits are equal to exactly the same as those 16 digits. I don't actually think it is. I don't actually think that's going to help us. Maybe it does in some way I can't see, but I don't think it's going to help us. Right, what on earth do we do now? That is the question. I don't know. There's something very major missing, though, from this, because I really have not, there's just not enough information here, unless it's possible to know what the composition of these, how can, I mean, even if we knew exactly what these 4 digits were, that wouldn't really, would it resolve the, I mean, if you knew the exact order of them, it might give you some data, some sort of information you could use. But I don't see how we can do that. Can I didn't check 9s on the diagonal, actually. Sorry, that's something I should have looked at. Let me just double check that and see if there was some something I could have spotted there. So, no, you see that, well, I don't know actually. Let's just highlight these squares. So if 9 is on the diagonal there, if 9 is here in box 1, it would be there in box 7. It would be here in box 9, and it would be here in box 3. So those 4 squares seem to correspond. If 9 is here, you'd get one there, there, there. That seems to work, doesn't it? Oh, this is just bifurcation now. This is not how I like to solve puzzles. There, there, and there. Which, oh, that one doesn't work. Okay, so 9 can't be there, I don't think, because if 9 is there, it goes here in box 3, here in box 7, sorry, box 9, and it has to go there in box 7, and look, it's clashing on that diagonal, so we can rule it out of that cell. That is not 9, which means 9 is on that diagonal, which means 9 is in one of those 2 cells. Which, so 9 is not here. But no, I don't feel like that's likely to be sort of, I don't like playing guess where the 9 goes, plot all its paths, and then see what happens after that. Let us think harder. Have we got set going on here? That's something I've thought about Fistimofel, but have we got some other set variation? If we try and get all of the arrows in the same sets, we could maybe do that. We could shift. Oh yeah, hang on, let's just think about that. Let's highlight all of these boxes and see what we have to subtract from these boxes to get to something interesting. So we know that those blue squares are 4 sets of the digits 1 to 9. Yeah, it looks to me like if I can remove those and those somehow, that might be interesting. Let's have a look at that. So if we, so let's agree these are 4 sets of the digits 1 to 9. If I was to remove from one of those 4 sets of the digits 1 to 9, these 3 digits and those 3 digits, in that set, what digits would I be left with? Clearly I'd be left with these 3 digits. So if you imagine, if we stack up, we've got one set of the digits 1 to 9 just here, another set below it, another set below it, another set below it. And from that top set, I'm just going to remove those 3 digits and those 3 digits. So that's 6 different digits. I'll obviously be left with those 3 digits. So I can remove those and plonk in those. Now I can do exactly the same with the second set of the digits 1 to 9 in my 4 complete sets. I'm going to do exactly the same and remove those. Or let's just stop actually. After having done 1, what do the blue squares now represent in this puzzle? Let's make sure we all understand that. So at the start, the blue squares were 4 sets of the digits 1 to 9. I removed 6 digits from there. So obviously, the blue squares at this point are equal to 3 sets of the digits 1 to 9, plus these 3 digits. But we don't know where these 3 digits are in blue. I've got no idea. I just know that they'll be in there somewhere along with 3 complete sets of the digits 1 to 9. So when I remove those cells from the second complete set of the digits 1 to 9, boom, like that, I'll be left with those 3 digits in that set, and therefore the blues at this point contain 2 sets of the digits 1 to 9, and these 6 cells somewhere. We don't know where they are, but again, they must be there. Now, let us continue with this by thinking about this row. And I'm going to remove from the third complete set of the digits 1 to 9 these four blue cells, whatever we find in those cells. So obviously in that set I will be left with these cells. So let's do that and see what that looks like. Boom, boom, boom. So now we know that the blues at this point are 1 complete set of the digits 1 to 9, and then these 4, and these 3 cells, so another 11 digits. So we should still have 20 digits in blue, and if you add them up, we do have 20 digits in blue. And now I'm going to remove these 4 blue cells from the last complete set of the digits 1 to 9, and I will be left with those, and that is some weird variant of the Fistomephel ring. Now, that looks interesting at first blush. Yeah, this is interesting. This is absolutely... That's a 9. That's our first digit. That is a 9. How do I know that this square is a 9? Well, let's think about what we know about this grid at this point. We know that the blues and the reds contain the same set of digits. I know that the reds have definitely got 2 9s in them. They've got a 9 in one of those 2 and a 9 in one of these 2. So where do these 2 9s go in the blues? Well, they can never go on an arrow. That's not going to work. You can't put 9 on any of these arrows without making these squares definitely greater than 9. So there are 4 possible positions for 9s, these 4 cells I've just outlined. But these 3, they all see each other. If you put a 9 here, you can't put a 9 in those 2 squares. If you put a 9 there, you can't put a 9 in those 2 squares because of the diagonal. So you can't put 2 9s in these 3 squares. So the second 9 must go here. That's forced. One of these 3 squares must be a 9. That feels like that is a massive breakthrough. The other thing we can say, yes, let's just carry on with the logic. This is really clever. So not only do I know that there are 2 9s in these 4 cells, I know that the other 2 cells are 7s or 8s. Well, I can't put 7s or 8s on the arrows either. For exactly the same reason I couldn't put 9 on them. They'll make the circles too large. So where do the 7s and 8s go? They will also have to go in those positions in blue. So these squares are actually a 7, 8, 9. No, I was about to say they can be selected from 7, 8, 9, but they are a 7, 8, 9 triple. They are a 7, 8, 9 triple because they see each other. So this is now getting quite profound, I think, because if we've got sorry, let me just think about this for a second. I've now definitely got, yeah, you can't put a repeated digit in these 3 squares because they see each other. So there must be 7, 8, 9 as a triple, which means these squares are now double 9, 7, and 8. Which is making me wonder all sorts of things. I'm now wondering whether I can actually work out what the blue arrows have to contain. So that's definitely something I want to look at. Let me just have a think and see whether I can do any Sudoku with this 9. Yeah, well, I can lock 9 into one of 2 places in box 7, because there's a 9 in one of those and there's a 9 here. I don't know if I can do anything else. Oh, I can do something. I can do a small thing. So is it possible there's another 9 in red? And the answer is no, because if I put another 9 in red, I've then got to put a 9 on an arrow, which I can't do. In fact, that's a better question perhaps, is red, these red cells here can't, not only can they not contain 9, they can't contain 7s or 8s either, because if they did, I'd have to put them in these squares where they cannot go because of the geometry trick that we've done. So in fact, in column 1 and column 9, I've got to have 7s, 8s and 9s not in red. This is going to get quite difficult to pencil mark. Oh, so what that means is in column 9, the 9 must be in one of those 2 squares, which means that square's not a 9, which means one of these 2 squares is now a 9 in column 2. Okay, I don't think I know. I don't think I know which one of those is correct. 9 in this column has got to be in one of those squares. Now, I could use the fact that the bifurcation gave me a 9 on this diagonal, didn't it? So I know that's not a 9, in which case I do know this is a 9 using that logic, but I don't really want to do that. Can I see another way of getting rid of the 9 from the central cell? You can sort of see it now. If you put the 9 here in the centre, that square will have to be a 9, and that square will have to be a 9. And now you've got nowhere to put a 9 in box 1 of the grid. You can sort of see that. Not sure. So basically we do sort of know this is a 9. Let me just think. Come on. I know these squares are 1s, 2s, 3s, 4s, 5s and 6s in some order. I know. Let's think about this. I'm wondering, we've done a few puzzles recently where the composition of digits on arrows has been important. I'm wondering if the same thing is going to be true here, because I know that one of these pairs, either this one or this one, is a 9-8 pair, and one of them is a 9-7 pair. But I also know that in selecting which version of 9 I use, for example, so say this was 9-7, because I don't know, the 9 and the 7 could be here, or they could be here, and they could be in either order. So it could be 9 here and 7 here. We don't know. But just for the sake of sort of analysis, we know that the 7 is for sure 1, 2, 4. And we know for certain that the 9 must only... this is really interesting. I see. Then I was going to say the 9 can only have one repeated digit with 1, 2 and 4. And that's true because otherwise this square has to have dual personality. So what is the composition of 9 that goes with the 7? It's not 1, 2, 6, because if it's 1, 2, 6, you've got a repeated 1 and 2. It's not 2, 3, 4, because that's repeating 2 and 4, and this would have to be a 2 and a 4. So it is 1, 3, 5, and the 1 is repeating only. And that's really interesting. So that means that wherever the 7, 9 pair goes, it goes with a 1 in the middle of it. I like that. I wonder if we can do the same. Let's just see if it works the same way with 8, 9 and the 8. It might be good now, because we know whichever one of these is 1 is going with 7 and 9. So we know it's a 2 that's going with 9 and 8. So the 2 is the only repeated digit that we're allowed to create. Now, that's beautiful, because that means that the 8 arrow cannot be 1, 3, 4, because there's no 2 in it, and there needs to be. So that's going to be 1, 2, 5. And now the 9 arrow can't be 1, 2, 6, so that's 2 repeated digits. And it can't be 1, 3, 5, because there's no 2 in it, so it's 2, 3, 4. So this... There's no 6. This is it. There's no 6. Oh my goodness me. Right. This is just brilliant. It's absolutely brilliant. So, whichever way up this goes, whether it's, we know the 7 and the 9 pair, which must exist either here and here or here and here, goes with a 1. We know the 9, 8 pair goes with a 2. And we know the composition of the arrows exactly. And look, there's no 6 in any of these squares. So what we've actually got is 3 1s, 3 2s, 2 3s, 2 4s, and 2 5s. And now I think we're getting somewhere. Maybe. Now the problem is I'm now going to have to delete all these digits, so I've got to try and commit them to memory. So 7... In the 7, 9 pair, we're using 1, 3, 5. In the 9, 8 pair, we're using 2, 3, 4, opposite 1, 2, 5. Because obviously we don't know which way round these go. But let's try and use the fact that we know there's no 6. There's no 6 in blue anywhere. So if there's no 6 in blue anywhere, these digits are now 1, 2, 3, 4, and 5. We know that they don't include 6 for the reason I've just mentioned. We know they can't include any 7s, 8s, and 9s, because we'd have to try and put 7s, 8s, and 9s on the arrows if there were any more 7s, 8s, and 9s. So these squares are 1s, 2s, this is sort of good levels of pencil marking, 1s, 2s, 3s, 4s, and 5s. I'm almost wondering whether I need to switch the highlighting now to low-high, because this makes me want to scan I think I am going to do that actually. I'm trying to keep track. You see, I now know that these 4 squares are high digits and these 4 squares are high digits. And what I'm trying to do in my head is work out whether I've got 4 high digits anywhere. And I can't quite see it. So no, I have. I have got 4. I've got 4 high digits on. No, I haven't. Not on. I have on this diagonal. I've got 4 high. Yeah. Okay. Sorry, I'm being completely inarticulate, but I'm getting excited about this because what I want to do now, I think, is to get rid of all blue highlighting in this puzzle. And the reason I want to do that is I want to convert every high digit into yellow. Okay, and now I'm going to highlight these ones in yellow. And now I'm going to show you something I noticed, which is that because I know that I've got 5 low digits in these columns, these squares, these dominoes here are all yellow. They're all high. I don't know. I don't know what they are, but I know they're selected from 6, 7s, 8s and 9s. Now, it doesn't seem to work on this diagonal because of the strange shape of this arrow, but on this diagonal, I've now got 4 high digits. So this has got to be 6, 7, 8 or 9. That's got to be 6, 7, 8 or 9. And more to the point, those 5 squares now all are red. So that's not 9. And now I've proved what I wanted to before. Look, now I can ask where 9 goes in row 5, and without having used bifurcation, I get my 9 here. Okay. 9 here is a high digit, so that can turn yellow. Now what do we do? Well, a simple thing I can do is ask where, yeah, I can't put all arrows using this definition have to turn red. So let's carry on with it. Oh, I've seen loads of stuff all of a sudden just by doing that. This square is now yellow. This column has got 5 low digits in it, so all of those turn yellow. This has now got 4 yellows in it. This is a good idea. This is working. I've got 5 reds in row 3, so that turns yellow. Oh, which we could have done from box 3. I've got, now on this diagonal, I've got 4 yellows. So the rest of it must be reds, I think. Which means that must be yellow. I've got five reds in the central box, so we need 4 yellows to complete that. I've got yellow. This is interesting. Surely that has to be... Surely, yeah, that does have to be low, doesn't it? Let's just look at the options for this square. This square can be 6, 7 or 8. It doesn't seem to be able to be 9. This square cannot be... This can't even be 8. Because if it's 8, this should be 9, which it can't be. So this is 6 or 7, which means this is not 6. So this has got to be 1 or 2 in order to complete... to make this arrow work, and if that's 1 or 2, it's most certainly red. Which feels like it might matter. Now, can we complete the colouring here? Don't know is the answer. Let me just think about this for a second. I feel like we might be... Oh, hang on. Is that right? Yes, it is right. Look. Oh, I see. Once this arrow, look, can't be a 6. Where do you put the 6 in row 7 of the grid? Because these could never be 6, you have to put 6 here. Which means I get a 7-8 domino at the end, which means I've got a... Look at this, I've now got a 6-9 pair at the top of column 9, which means that must be a 7 or an 8. This square now has to be red by elimination. You can see it's not 9 and it's not 6, 7 or 8, so that's red. That gives me all the reds in row 5, so that's got to be yellow. Oh, in fact, look, both those are yellow as well. We've got 5 reds in column 7. So this is a high digit that's not 9. That's 6, 7 or 8. And that's a low. Oh, I think this has got lots of options by the looks of it, which is a bit distressing. Where does 6 go? Oh, this is massive. Oh my goodness. Where does 6 go? I've just noticed I've got a 7, 8, 9 triple in column 2. So 6 is in one of those squares. Don't know which one. But that means it's not there. So that must be 7. And once this is 7, this must be 8 and this must be 1. which means there's no 1s in there. We can remove 8 from both of those squares. So this is 6, 7 or 9 now. This is not 8. I've got to keep track of these diagonals as well. Yeah, in fact, I do have to keep track of the diagonals because where does 8 go on that diagonal? It doesn't seem to be able to go there because of, yeah, there's some 7, 8 pair here. So 8 goes here, 7 goes here. 7 is removed from these squares. This is beautiful. This is beautiful because now, well, not only is this a 6 by elimination, and that must be 8 by an elimination just to complete the high digits. That's not 8 anymore. But more importantly, this is an 8-9 pair. What number goes between the 8 and the 9? It was the 2, which means 1 goes here, and this must be the 7-9 pair. Oh, and we could have seen that once we got the 8 there. So this is all beautiful now. How long have I had? 41 minutes. That's not too bad for this puzzle, I think. This is hard. It's also incredibly interesting. Now, what do we do next? This has got to be a 7, 8 or a 9, I think, just by, and the same with this square. So the 8 is in one of those, which is not telling us anything new. This square can't be a 1, look, because of this one here. I'm just looking at 1 in column 1, which has now got to be in that square exactly. I mean, that's not a 1. This is not a 1. Oh, I see. Oh my goodness. Right, this 1, where does it go in box 3? The answer is I don't know, but I do know it's on the arrow. Now, why does this matter? It matters because of what we did earlier with the 9 and the 8. Where you had the 9-8 pair, you had to have the 9 being a 2, 3, 4 and the 8 being a 1, 2, 5. That was the only way it worked, so that you only repeated one digit, which was the 2, which you needed to be the repeated digit. So now I think that means that's an 8, because the 9 needs 2, 3, 4 and not a 1. So I think that we can do that. This becomes a 5. This is 1, 2, 5. So this is not 2, 5. This is 3 or 4. Get rid of the 1s in the corner there. Now, is that what we needed to get the puzzle finished? The answer is I don't know. 5, look, now has to be in one of those squares. So 5 is not here. And that's not 9 because of this 9 here. Oh, hang on. Oh no, that's fine. I was thinking this diagonal must be resolved in some way, but I don't think it is. 9 can't go here on this diagonal because the 9 must be on one of those two squares. So we can get rid of 9 from this square. And that 8 is pointing at that square. Let me just double check the logic there. Is that right? In this diagonal, I've got a 7, 8, 9 triple left to place. The 9 definitely has to be here, so it can't be here. This can't be an 8 either, and it can't be a 6. That is a naked single. 7, 9, 8 go into the grid. 9 and 6 can be placed. 7 and 8 can be placed. 6 can be placed. 7 can be placed. 9 can be placed. And the expression we are looking for is good grief. That's a 9, that's a 7. That 9 and 7 is lovely, because now I know that's a 1, 2, 4 triple, which means this is a 3. This square must be a 5. That looks like it's working, doesn't it? So this is not 3 or 5. Oh, not 3 or 5. This has got to be a 2 or a 4. This arrow is 1, 3 and 5, which is exactly what we'd expect it to be. because that adds up to 9. And look, there's only one repeated digit, which is the one that we're looking for. Now, what should we look for now? That's the next question. I don't know is the answer. Have we got any more wins that we can accomplish using the yellow squares? These squares are 6, 7s and 8s. That's not 7. Don't know is the answer. What's the central square of the grid? Hang on, that's seeing 1, 2 and 5 I've just noticed. That's a 3 or a 4. Whoa! There's a 3, 4 pair on this diagonal now. So this is a 1, 2 pair. Which means these are 3, 4 and 5. Oh, this is gorgeous. Look at this diagonal now. Once you get the 3, 4, 5 pair here, that becomes resolved. Oh, this is it's going crazy. That's going to be a 1. Look. Yeah, this 4 is giving me a 4 here and a 3 here. That's bouncing back into the middle, giving me a 3 in the centre. There's no 3 or 4 on these arrows now. This square cannot be 1, 2 or 5. So that, oh, it's just forced. That's a 4. Oh, and this can't be a 3. 3 is not available as an option, so this is a 6. That's a 2. This is a 1. This is a 5. This is a 1. This is a 2. I'm almost lost for words at this. This is one of the most extraordinary Sudokus I've ever seen. It is ridiculously clever. This is an 8. This is a 7. I was on the verge of switching the camera off and calling Mark to check whether or not I'd been given the right puzzle here, because I couldn't believe this solved, but I think it is doing. This is a 2. That is a 2 by Sudoku. It sees 4 and 5. Oh, look, we've got 4s and 5s all over the place now. What about those squares? What are those? They are 3 and 9. I'm not sure if I can do that. No doubt some people will shout at me if I should be able to do it. I can't see how I can do that. Those squares are 3 and 6. Oh, so that's sort of... Oh, how am I going to disambiguate all this then? That's an interesting question. There must be something we can do here to get to the bottom of things. What is that? Oh, it's this 2, I suspect. Let's see if that's going to help. Yeah, that gives me a few 2s, look, dotted around the place. This 2 up here gives me a 2 in there. That gives me a 1 and a 4. That gives me a 4 and a 3. The 1, 5 here gives me a 5 here and a 3 here. And this 7, I was wondering how this was going to work. 7, 9, 9, 3, 3, 6. Thank goodness for that. And I can see the 4 and 5s can be disambiguated by something going on in one of those positions. So that should be fine now. Let's have a look. 3, 4 and 8 into those squares. And we can place the 8 by Sudoku. And we get a 3, 4 pair. And these squares are 2, 5 and 6. And the 2 must go here. The 6 must go here, the 5 must go here. Now, 6's have got to be there, exactly there. These squares are 1, 5s and 7s. So this square's a 5. 5 and 1 go in, 7 and 1 go in. This is a 3, 4 pair, and the 3 in the middle is going to be useful. I don't believe it. I think I've solved the puzzle. Now, 9s should all be yellow. 8s should all be yellow. 6s should all be yellow. 7 should all be yellow. And everything else should be red. Let's just do that. And then we can stare at it in admiration. 2s. Red. I think this is the solution. No, I messed it up. Oh no. Oh, just because I've not done the 4s and the 5s. Okay, I'll forgive myself that. 5, 5, 4, 4, tick. Yes. Good grief. That is one of the great puzzles you will ever see. Aaron Rodgers, take a bow. GB Pack, take a bow. I'm astonished by that. That is just amazing. So this weird collection of arrows did more work than you can shake a stick at. I should do the Aaron Rodgers celebration, shouldn't I? Is that... There you go, I did it in my own inimitable way. That is amazing. I'm sort of... it's just astonishing that whittling down the possibilities because of the way that the arrows impact the repeated digits, and then doing a sort of modified version of Fistamafel, which was huge actually, because that did allow me to place the 9 here, didn't it? And to conclude things about the relative positions of high digits. But what I absolutely loved, to be honest, was figuring out that these cells couldn't contain a 6. That was just such a revelation. So once we got that, we got all of these yellow squares done in various places, and then I spotted one of the diagonals just had yellows on it, and that was marvellous. It's just stunning. The puzzle quality at the moment is off the charts. Thanks so much for watching. It's another longish video. I apologise for that. My brain doesn't take me any faster, however much you might like it to. And we'll be back later with another edition of Cracking the Cryptic.